Let me begin by thanking the organizers for putting this wonderful meeting together and inviting me to speak in it. In trying to decide what I was going to talk about in this meeting, I sort of looked, I noticed that Deepak was going to talk about multiple phase transitions. And I said, okay, that sounds like a good idea. So I can also talk about a system with interesting multiple phase transitions. And that's what I'm going to tell you. I think the similarity begins and ends there. Nevertheless, this is something that we pursued over many years, but more importantly, we've been sort of trying to do something in the recent past. So I thought this was an appropriate topic. Yeah, great. Okay, so here's the outline of my talk. I will begin by sort of saying something by way of a broad introduction to the idea of liquid-liquid transitions in single component fluids. And these all belong to a certain class of substances which have open tetrahedral sort of local order, water being the prominent example for which this idea was originally floated. And subsequently, there have been many other systems in which this has been explored. And over time, this possibility of liquid-liquid transitions being the origin of interesting behavior has also been pursued in several other soft matter systems. And by a little bit of a stretch, one could include the recent interest in liquid-liquid phase separation in biological assembly, though the physics there is likely to be very different. Okay, so this is sort of a very special example of a basic phenomenon in condensed matter, in the sense that the discovery of this phenomenon was done through computer simulations. So it's not a very uncommon thing in hard sphere fluids as well. The possibility of crystallization was first realized through computer simulation studies. And so the liquid-liquid transition also belongs in that category. Starting with initial computer simulations in water, and then subsequently in substances like silica, SiO2, and silicon, which is what I'm going to be talking about, atomic silicon. There was a gathering of simulation evidence to probe this possibility, and enough evidence was gathered that the people who wanted to believe were convinced that such a transition was genuine and it existed. The sort of the one relevant detail going forward is that these transitions occur in the metastable liquid, and therefore sort of its standing as a genuine phase transition one should take seriously is always a little bit in question. And okay, I hope Nivedita will get back whether it's better now. Okay. Okay, great. So one of the questions that subsequently was raised was whether indeed there was a genuine transition between two forms of the liquid, or whether slow spontaneous crystallization was being misinterpreted as the formation of a second liquid phase. And the people who raised these questions also sort of raised the bar on the kind of evidence that you needed to produce to sort of claim that there were two liquid forms, which was to say that you needed to do that you needed to do fairly detailed free energy surface calculations and show the existence of free energy minima that are associated with the different liquid states in order to claim that there's a liquid-liquid transition. And indeed, this has been very helpful because this sort of made people work harder and generate such evidence. And from our own work in the case of silicon, which is a bit of an extreme case because this is unlike water, which forms hydrogen bonds that are fairly floppy and flexible, and also silica, which has a bridging oxygen between the silicon atoms. In silicon, the angular correlations are very stiff. They're not floppy. And so it is much more prone to crystallization, and therefore the kind of skepticism that has been expressed in literature is more warranted in this case. It also makes it harder to establish that there is indeed a metastable liquid-liquid transition. But the summary of our work in this is to indeed show that there are finite barriers to crystallization, and therefore no spontaneous crystallization in that sense. But these barriers are low. So we've also then constructed free energy, two-dimensional free energy surfaces to demonstrate explicitly that there are two liquid forms. And it turns out that the sort of the spoiler in this is that is going back to the work of Limmer and Chandler, who were the ones who raised these questions about whether there were indeed two liquid forms, is that the choice of the order parameter to characterize crystallinity proves to be, or the choice that they made proves to be problematic. So in the end, after like a decade of controversy about this, the summary is that there were sort of two choices of simulation methodology that they made, both of which turned out to be problematic. In the case of water, they used a method which is fairly well established for accelerating simulations, which was a hybrid Monte Carlo method, but their thermostating had a problem, and as a result, their results for the case of water turned out to be erroneous. And in the case of silicon, it turns out instead that the choice of order parameter used to construct the free energy surfaces has problems, and I'll say a little bit more about it. And as a result, their conclusions were not valid. Okay, so the work that I'm going to talk about, as I mentioned earlier, has been pursued over many years. But the latest round of this, which is what I'll talk about today, was the PhD thesis of a student, Yagik Goswami, who's graduated since and has moved on to better and other things. This was also done in collaboration with a former student, Vishwas Vasisht, and with Dan Frenkel and Pablo De Benedetti on the crystallization barrier work. So these are works that are published in the last year, this year and last year. Okay, so even though I'm going to be talking about silicon, liquid silicon is not a very familiar substance. And so it's sort of easier to get going by talking about the anomalies in the case of water, which also was the substance for which the liquid-liquid transition scenario was proposed. And there are many, many anomalies to talk about. but the main point is simply to say that starting with the density maximum in water and the compressibility minimum, the heat capacity minimum, which all occur at ambient conditions, there are a number of ways in which the liquids that belong in this category of tetrahedrally coordinated substances are anomalous. And there has been a long-standing interest, particularly in the case of water, to try and understand the origins of these anomalies. So one of the explanations that was proposed way back now 30 years ago was based on computer simulations. The data for that is shown here. These are simulations where liquid water and water at much lower temperatures was compressed. And the observation was that instead of the volume decreasing sort of gradually as the pressure was increased, there was sort of a sudden jump in the volume or the density, indicating some kind of two-state behavior. Now, these are actually highly out of equilibrium simulations. The liquid isotherms are shown further below, and what they revealed instead was the development of an inflection, which usually precedes, as you come up from high temperatures, the approach to a critical point. Okay, and based on such simulation results, there was a proposal in the case of water. For some reason, the temperature is put on the y-axis in these phase diagrams, which is a bit confusing, and pressure is on the x-axis. So there was a proposal that in addition to the familiar liquid-gas critical point, there exists a second liquid-liquid critical point. But unfortunately, under conditions where the lifetimes are fairly small, so that the dashed lines here sort of indicate the boundaries within which crystallization kinetics is very rapid. And that makes it difficult to sort of obtain direct experimental evidence. Okay, so as I mentioned, this was a proposal for water, and many other substances have also been then presented as candidates for exhibiting this liquid-liquid transition because of their similarities in properties with water. And one such substance which has been is there, I mean, I can just operate it from here. Yeah, okay. Sound is fluctuating. Yeah, okay. So one such substance that we have been interested in is silicon, which, like water, has an open tetrahedral geometry as the energetically preferred structure, and a solid phase that is of lower density than the liquid. This is just a cartoon of the diamond cubic lattice structure that silicon has. And this material has been studied using a classical empirical potential called the Stillinger-Weber potential, which is a sum of 2- and 3-body interactions, and that are sketched here. Basically, in addition to a 2-body attractive interaction, you have a 3-body repulsive interaction, which penalizes deviations away from the tetrahedral angle when you consider 3 atoms. And okay, so this from early simulation evidence, such as what I've shown here, we had concluded that silicon does indeed exhibit a liquid-liquid transition. So just to quickly run through, these are simulations done at constant enthalpy, which if you were to go through a transition you expect will show non-monotonic behavior. And indeed, that does happen both for the liquid to crystal transition at equilibrium, as well as this liquid-liquid transition. And, and in the literature, experimental literature, actually, there had been long a discussion of a liquid to amorphous transition. So one of the things we checked was that the lower temperature phase was of finite diffusivity. And of course, the low temperature liquid has tetrahedral ordering. And further work, again, in our group, showed more sort of evidence supporting this possibility. And based on the simulation results, we were able to construct a phase diagram. So one of the evidences was the compressibility as a function of pressure as one lowered the temperature, which became sharper and grew in magnitude. And this in turn corresponded to a flattening of the isotherms as one approached temperatures close to the extrapolated critical point, and then one could observe a discontinuous change. Okay, so this is just, I think this is the only H bar not equal to 0 work that I've been involved with, so I have to show it. So there's also interesting changes in electronic structure with a pseudo gap developing in the low temperature liquid phase. Okay, all right. So as I said, evidence such as what I showed for silicon was questioned at a later point in time by Limmer and Chandler, who performed free energy calculations, and they argued that you need to do that in order to get the true picture, and sort of had some idea of how slow crystallization might be the culprit for people like us to misinterpret what was going on. And so they constructed these free energy surfaces in density Q6, which is the global bond orientational order parameter, which if necessary, I'll sort of describe later on, but it basically measures bond orientational order and therefore a crystalline order. And so what they showed was that at temperatures and pressures where people had earlier claimed to see a liquid-liquid transition, they had only one free energy minimum that corresponded to the liquid, and this deeper minimum corresponds to the crystal. And likewise, and more mysteriously, they claimed that for the Stillinger-Weber Silicon that we studied, there was in fact no free energy minimum at all that corresponded to a liquid. And this was very surprising. And it turns out that, okay, so the work called into question all the previous evidence for the liquid-liquid transition in water and silicon. And as I said, it turns out central, I mean, there were sort of very particular reasons why that it turns out to be wrong. And in our case, okay. All right, I'll come to this in a minute. Okay, so in the case of water, there's been a lot of work to sort of establish that indeed there is a liquid-liquid critical point. So this is the corresponding free energy surface that was constructed in the group of Pablo De Benedetti and co-workers, which shows clearly that at appropriate conditions, there are these two free energy minima that correspond to a high density and a low density liquid phase. And more recent work has sort of has looked at the corresponding sort of critical behavior, identifying a suitable order parameter, which is a linear combination of the density and the energy to distinguish the two liquid phases, and sort of some not so direct, but okay, some analysis to suggest that this is a transition in the Ising universality class. It shouldn't be surprising, but that's been done. And more interestingly, perhaps, there's been some very sort of fast pump probe kind of experiments, which reveal that indeed there is a large or meaningful window of time, though all in nanoseconds, where one observes a transformation of this initial high density liquid phase to the low density liquid phase much before the crystallization that is shown in this shaded blue sets in. Okay. Okay, and this I'll skip over, but just to say that again, over many years of work, there's also corresponding evidence in the case of silica. And so that brings us to silicon. So what about silicon? And as I mentioned already, the work of Limmer and Chandler claimed that there was indeed no free energy minimum at all corresponding to the liquid phase at conditions where other people like us had performed simulations and thought that there was a metastable liquid that had a finite lifetime. And so one of the things that we, as in Ritchie and company, considered was redoing the same simulations that they had done. And what we found to our puzzlement was that indeed they seemed to be right, because we also didn't find in the conditions that they had studied a free energy minimum corresponding to the liquid phase. And and this was, I mean, we were puzzled rather than sure about what it meant, because we had much experience with simulations performed under these conditions where one had the persistence of either the HDL, the high density or the low density liquid over sort of order of hundreds of nanoseconds simulations, which are simulations go very long, even though it may not be a very long time for an experimental system. And it turns out that the reason for this is that the global order parameter to characterize crystallinity turns out to be a problem. And so let me just sort of begin by illustrating that. The basic idea is when you perform simulations to access either difficult to access regions in the order parameter space, or you want to sort of systematically sample, you use the procedure of umbrella sampling, where you introduce a bias potential that restricts your system in a certain range of the order parameters, and then you sort of remove the bias. And I'm not going through the details of that because it's probably quite familiar. But the thing that is important to ensure is that the bias does what you think it's supposed to do, right? So here, if I put a bias at a certain value of the global Q6, I want that fraction of the system to be crystalline, right? But it turns out that the Q6 values that I measure in simulations vastly underestimate the amount of crystallinity present in the system, because I can have a configuration like this. This is a cartoon where I have all these blue regions being in perfectly crystalline order, but they are not part of the same crystallite. They're misoriented with respect to each other. And when you have this kind of polycrystallinity, you can end up having a low global Q6 value, but a high, high crystalline order, right? And so, in fact, when the system is not subjected to any kind of biasing, this doesn't seem to be a problem because it'll do whatever it does. So here I show for silicon simulations, the result of runs which are done without biasing, where I look at sort of both these measures, the size of the clusters and the size of the crystallites. The clusters are basically the sum of all of these, whereas a crystallite would be one of these, right? So I look at the distribution of crystallites I have, or crystalline clusters I have, and they pretty much are the same when I don't apply a bias potential, whereas when I do apply the bias potential, the distribution of clusters extend to much larger values, excuse me, than the distribution of the size of crystallites. And when you do, so as a result, the global Q6 that you're measuring is not giving you the correct picture. So let me not belabor this point, but this is sort of like a central point that came out of our early investigations in this round. So then we said, okay, so the one way I know how to calculate crystallization barriers is to do umbrella sampling. But if I can't do it because I muck up my sampling in ways that was not anticipated, what else can I do? So there are two answers to this, both of which we have explored. One of which is see if you can estimate the free energy surface or the free energy barriers with unbiased simulations, where you don't when you let the trajectories go from the initial liquid state to the crystal final state and reconstruct free energy barriers, or you choose more sensible order parameters with which to do your biased simulations. And so for the first method, it turns out there is a very useful approach that has been proposed in the literature, where if you assume that the dynamics of your system along the relevant order parameter is well described by a Smoluchowski equation, then you can sort of, in 1D, you have an expression for the mean first passage time in terms of the free energy surface, and you can invert this relationship so that if you measure in simulation the stationary distribution along that one coordinate as well as the mean first passage times, you can then reconstruct the free energy profile from this data. Okay, so we're not trying to solve these equations. Well, we're doing the inverse problem, so we can't. But the idea is, if there are things that you can measure cleanly in simulation, such as the stationary distribution and the mean first passage time, can I then use it to obtain the free energy profile, which is, I guess, in some context, usually the input, but this is what we want to derive from our simulations. And so this is indeed what we do. How do you estimate the D of X? Okay, that's a good question. We don't, but so it's not assumed to be constant, number one. And secondly, in fact, if once you know the mean first passage time or the derivative of the mean first passage time on this quantity B, the D of X is expressible in terms of that. So we can actually calculate it a posteriori from the same approach. Yeah, no, that's usually that's something that's swept under the rug. Here it's not. It's something that you can calculate. And indeed, in the crystal nucleation problem, the D of X, where X is the degree of crystallinity, is a function of the size of your nucleus, right? Because it depends on the attachment surface area. Yeah, okay. Okay, so the first question then is using, okay, so the second method that we employed to cross-check was using a different order parameter, which is the size of the largest crystalline cluster. Okay, this is something that is conventionally, in fact, used in this literature. So we went back to that. And so we had free energy profiles. It's a little bit busy, so let me just walk you through it. So the black dots are the free energy curves as a function of the size of the largest crystalline cluster, which is also the order parameter in this mean first passage way of doing the calculation. And we did umbrella sampling with the same order parameter, which is the red curves. And but without going into the details, because I think, whoa, okay, not so good. I think I'm running out of time. You can also compute the free energy profiles not as a function of the largest cluster size, but as a function of the size of crystalline clusters that may be present. But doing all this, basically, the summary is you do end up getting consistent estimates of the free energy barriers, and they're finite, both above where we expect the liquid-liquid transition and below where we expect the liquid-liquid transition. Okay. And something that's sort of an interesting aside is even though these critical nucleus sizes are small, it turns out that the relationship between the free energy barrier and the critical nucleus size expected from classical nucleation theory continues to hold to fairly low temperatures. And you find deviations away from it when you go from the high density liquid to the low density liquid side. Okay, but I shouldn't dwell on that. Okay, so what about the liquid-liquid transition? Let me quickly go to that. This is now a picture that shows what if you have a phase diagram as I've sketched here with the pressure on the y-axis and the temperature on the x-axis, a critical point here, and a line, first order line going up that way. If I look at these different points, what I expect to find in density as the free energy surface are shown here. So if I'm above the liquid-liquid transition, I should find only one minimum. If I'm exactly at the liquid-liquid transition, I should find a double well structure. If I'm below the liquid-liquid transition, I should also find a single minimum, but not at the same place. Okay, so the density is lower. On the other hand, if I'm sitting at some point which is supercritical, then I should find a flatter free energy minimum that sort of gradually moves as I vary the temperature or the pressure. Okay, so I'm sort of not dwelling on a lot of pretty hard simulation details, but this is basically data to show that if I simply look at the free energy barriers along the crystallization order parameter for all the simulations that we've done, which are at higher pressures than the data that I showed earlier, I do have finite free energy barriers. And then if I stay at small degrees of crystallinity and I look across density, I find this structure where I begin at high temperatures with a single free energy minimum. And as I lower the temperature, I develop the double minimum structure. And if I keep going further down, I end up with a single minimum again, but at a lower density. Okay, so this is clear. And this is the two-dimensional free energy surface, which indicates the same. Okay, and we've also sort of done the analysis of the kind that I mentioned earlier had been done for the case of water, where we look at sort of the bimodality of distributions in the density energy plane, use this to construct an order parameter with respect to which we can look at the distribution function, compare it with the, actually we don't so much do this as a test of the Ising universality class as comparing with an empirical distribution that has been proposed for the Ising universality class to identify where our PC and TC is. Okay, and this is now showing system size dependence, because if you look at a double well structure at coexistence between two phases, the surface tension gives you the size of the height, height of the barrier, and it scales with the system as the surface area, and that scaling is indeed something that we find to a very good extent. And similarly, the crystallinity in the system you expect will decay as okay. All right, so I'll wrap up very quickly. So all of these results taken together offer a compelling evidence of a liquid-liquid transition in silicon at a level that's comparable to the work that has been in the case of water. Now, the next part is something that I wanted to spend some time on, but I'll sort of say it very quickly, maybe it's something to discuss with people offline. So one thing that came up in this work, as I mentioned, is the importance, at least in special cases, of being able to compute free energies using unbiased simulation trajectories. Now, the result that we used, or people had used, which we borrowed, used an expression for the mean first passage time in a 1D problem where the result is known. But if one has a higher order parameter space, we don't quite know, we can't use that result because when we sort of pretend, well, not pretend as David did, but assume as David did in part of the discussion that you have Boltzmann sampling along the other directions, it doesn't work, right? You don't have Boltzmann sampling when you have an absorbing boundary condition, and therefore you have to, oh, I guess that's a sign from somebody. So we've sort of been trying to play with ways of looking at sort of fluxes and transition rates between pairs of states and trying to sort of use the ratios of transition rates, which give you, through detailed balance, gives you the ratio of equilibrium probabilities, but use it in a steady state condition with absorbing boundaries to see how well we do. And it turns out we do rather well for the toy problem on which we've been trying to do this. You can reconstruct the free energy surface along the second axis quite well. Seems to work well for silicon as well up to a point, but we are facing sort of, it doesn't work well enough at this point. They're both possibly conceptual or simply sampling issues that we need to overcome, which we are working on. I sort of wanted to put that up simply to say if people in this audience have better ideas on how to go about this, this would be a very welcome suggestion. The problem statement is that from quantities that are measurable in simulations, we want to reconstruct the free energy surface. It's a simply stated problem with a higher than one order parameter space. Okay, so let me stop there. Not too bad. And I'll be happy to answer any questions. Thank you.
Thank you, Srikanth, for the... We have time to go. Yeah, first break. So
technology of water and silicon continue, because if I understood correctly, this liquid transition in water was discussed for this at 4-degree temperature, right? Super cooled water behavior, no? Anyway, so okay, so I misunderstood. But then the question is that how far this analogy pursue? For example, we have seen a lot of low temperature anomalies in silica or in silicon. And do you think that this super cooled behavior of water can also have some kind of analogy with 4-degree temperature behavior of silica?
In 4-degree Kelvin?
Yeah, 4-degree Kelvin.
Okay. So I can only give a very sort of indirect and speculative answer.
I mean, just anomalous behavior of one case can be mapped to anomalous behavior of the other case. That's a question.
So when you talk about low temperature anomalous behavior, you're talking about amorphous ice or amorphous silicon or silica, right?
Boson peak behavior, for example.
Behavior. See, this has to do with the presence of defects, as people understand. And there will be some influence of the existence of a liquid-liquid transition on the extent of the defect population at very low temperatures, right? So to that extent, the analogy will carry, but a lot of details differ because in silicon, the crystallization kinetics is very rapid experimentally. In the case of silica, it's probably the easiest, right? So yeah, I mean, I can only.
Maybe you need a new theory to look at supercooled behavior of water, similar to silica.
No, that I don't, I mean, maybe, of course, but I don't see that as being necessary. But low temperature behavior, I mean, right now there's sort of some work on revisiting low temperature behavior of glasses in sort of atomic glass formers. I think for open framework liquids, this behavior is likely to be different, and that does need a relook. And I think, like I said, the presence of a liquid-liquid transition will say something about the defect population at low temperatures.
Yeah, Srikanth, so the question is for both water and silicon. What is are there any structural and rheological differences between the high density and low density forms of these?
I mean, structural, obviously. And in fact, there's something that something that was always bothersome to me was sort of this hand-waving statement about more tetrahedral or less tetrahedral. It didn't seem satisfying enough. But there's some recent interesting work.
Sorry, the follow-up question was: should you be thinking of these as liquid of tetrahedra, or?
Yeah, so okay, that's what I'm going to say. So there's interesting work that shows that there are actually topological characteristics that are distinct in the two liquid phases. So it's sort of there's a, I mean, actually sort of my advisor Jean would make these sort of hand gestures to sort of tell the difference, where if you think of these two as water molecules, you would say they're either like this or they're like this. And it was always kind of funny because it didn't go beyond that. But that does say that is a way of starting to think about interpenetrating tetrahedral networks versus non-interpenetrating tetrahedral networks. And now people are beginning to sort of make that as a more precise statement, as a change in topology. And we're also doing that for silicon, but we're just getting going. Rheology is something very interesting. Yeah, that's sort of a long pending problem that we haven't. I mean, once, yeah, I'm sure the plasticity is different in the two cases. I don't know to what extent it's been studied. That would be interesting. We should talk.
Considering time, we'll take one last question from Satya.
So you talked about the NMAX at some point, right?
Hmm.
So how does the NMAX vary as you approach?
I mean,
the size of the largest cluster, does it diverge, or what does it do? I mean,
yeah, no idea. I think, when you look at, I mean, so when you look at crystal nucleation with whatever order parameter, the NMAX, you sort of, the ideal case that you have in mind is that one nucleus forms and grows, right? So because we are deeply supercooled, we're already away from that idealized picture, right? Because you don't form and grow, crystallize to very large sizes. Now, what you're asking, I mean, if you go near the critical point, you'll have density fluctuations. You'll presumably have crystal order fluctuations. I mean, we haven't looked at it. I don't know if anybody has. Those distributions will probably be much more complex. Yeah. Okay. But do you have a reason to be interested? Okay.
Okay, so considering time, I encourage the rest of the questions to be continued on the break. So our next speaker is
wait. Can I just sort of, okay, I mean, I wanted to acknowledge my past co-workers, which I didn't, but I also wanted to take this opportunity. There'll be time to say more later on, but I wanted to thank Deepak for all the inspiration that he has provided so many of us, and to say congratulations.